Hello students, this is the continuation of 10th lecture and we were discussing about the dynamic similarities, and we have also said that for a model to be dynamically similar with the prototype, first it must be kinematically as well as it should be geometrically similar. Then only we would call the model as dynamically similar, or the ratio of all the forces acting at a homologous part are equal. And we have also said that ratios of forces are nothing but these are the items, because the ratios of forces will not have any unit. Yes, because all the forces are of is expressed in terms of Newton divided by Newton will be dimensionless. So let's discuss about different types of forces in fluid mechanics. Number one is the inertial force, and it is defined by mass into acceleration. And further you can go on deriving, and finally you will get inertial force is density times characteristic length square times velocity square. But it is not important at this point of time to go into this derivation, but just understand there is a inertial force, and inertial force is nothing but it is the mass into acceleration. Moving on, we have frictional forces. Now these frictional forces, or the viscous force, we are saying this frictional force in terms of fluid, okay? And these viscous force are nothing but when fluid, when there is a motion in a liquid. So actually there are layers of liquid which glides over one another. So what is the friction between these two layers is what is known as viscous force, and which is expressed as tau times A. And this tau itself is the product of a coefficient times the velocity gradient, and this coefficient is the dynamic viscosity. And finally you can express the viscous force or the frictional force as mu, v, and l. So where this mu is the viscosity, v is the velocity, l is the length characteristics. Now next is the gravity force. Now this gravity force is the weight, right? Weight of an object is also known as the gravity force, and it is defined as mass times acceleration due to gravity, which is further you can go on into this and you will get uh, density times L cube times acceleration due to gravity. So this is the gravity force. Next force on the list is the pressure force. Now pressure force is nothing but pressure intensity times the area on which it's acting. So this is the resultant force uh, because of the pressure. Okay, so because of the pressure intensity. So this is the resultant force because of the pressure. Next force is the elastic force, is defined as bulk modulus elasticity times the area. And we have the surface tension forces. Surface tension forces is it exists in the water surface, in a water bubble. So these forces are the surface tension forces. Now let's discuss about their ratios. Now number one we have is the well-known, that is the Reynolds number, and it is nothing but it is the force, is the ratio of inertial force to the viscous force. And this is uh, the Reynolds number. Reynolds number is defined as the ratio of inertial force to the viscous force, and you can express this force in terms of its dimension, and then finally you can get the expression for Reynolds number. Here nu is the density over mu, which is the dynamic viscosity, and here I have expressed in terms of mu. Now you may be confused about this characteristic length. You have studied Reynolds number with the parameter d, which is the diameter of a pipe, right? So whereas here I have written L, so please don't be confused here. It is here we are playing with the dimensions, so d is also a length, so you can express dimensionally it is L. So here I have expressed that L, it could be it could be diameter in terms of pipe flow. Now, what a Reynolds model law says is, for a flow condition, if inertial flows and viscous force are predominant, the similarities of the flow in the model and its prototype can be established if Reynolds number is same for both the system. So what it's saying is, for a model to be dynamically similar with the prototype, the Reynolds model law must be satisfied, meaning the Reynolds number of the flow in the model should be equal to the Reynolds number of the flow in the prototype. And you can express Reynolds number in terms of its dimension, and then you can equate it. With this, let's solve a small problem. The problem is, the aerodynamic drag of a new sports car is to be predicted at a speed of 80 km per hour at an air temperature of 25 degrees centigrade. Automotive engineers build one-fifth scale of the car to test in a wind tunnel. It is winter and the wind tunnel is located in an unheated building. The temperature of wind tunnel air is about 5 degrees centigrade. Determine how fast the engineer should run the wind tunnel in order to achieve similarities between the model and the prototype. So the question what it's saying is, there is a sports car which company wants to build it, but it wants to test its performance when it is traveling at 80 km per hour. In particular, it wants to test what kind of drag force, how much drag force the sports car is going to get. Going to, it is drag force is going to be that there is a drag to the sports car when it's traveling at 80 km per hour at a temperature of 25 degrees centigrade. And the setup for the model is, there is a wind tunnel. Wind tunnel is a simple device where wind will be blown from one end of the tunnel. In between, you will place your model and then you will do the experiment. And here, the setup is, the air temperature is only 5 degrees centigrade, and the model ratio, the length ratio is 1/5 scale model, meaning it is just 1/5 of the actual car. So with this much of information, let's try to predict how much drag this sports car may receive when it's traveling at 80 km per hour. Now, to approach this problem, first we list down all the information that is provided. The the property of air at 25 degrees centigrade is given. Okay, the property of air when temperature is 5 degrees is also given. Now, to approach this problem, we have to use model law, because for it to be similar, it has to satisfy the model law. Now, which model law should we approach with? I mean, to approach this problem, which model law should we use? So here in this question, the viscous force and inertial force are the predominant forces here. So we can directly use Reynolds number. But for purpose of this question, let's understand beyond this. Okay. For this, what I have done is, first let's try to establish that Reynolds number actually holds for this situation. For this, we have to do the dimensional analysis, and I'm pretty sure one of the pi term will be Reynolds number. Let's check it out. So the drag force depends upon density, velocity, length, and the viscosity. Yes, this is velocity, this is viscosity. So there are how many parameters? 1, 2, 3, 4, and 5. So there are 5 variables and m known variables lm and t3. So number of pi terms becomes 5 minus 3, that is 2. So pi 1 and pi 2. So there are 2 pi terms. Now let's solve for pi 1. So I am taking 3 repeating variable with mu s as another variable, and here, while selecting this repeating variable, we should remember that one of the parameters should be the fluid property, where density is the fluid property. One of the characteristics should be the flow. Here I have taken velocity as the flow. Another one should be geometric. Here I have taken as M. By solving this, we get to know that pi 1 is indeed the Reynolds number. See, we proved it. So Reynolds number should hold good for the model and the prototype. So how do you solve this problem now? We express Reynolds number in terms of formula. of prototype should be equal to model. Here, all the informations are provided except for length of model and length of prototype is provided, but in terms of length ratio, which is the scale, which is also provided, which is given as 1:5. So we make Vm, the velocity of the model, as the subject, and then we solve this equation and we get this solution as this much. So you can try this out yourself. Next type of the ratio is the inertial versus inertial by the gravity force, which is also known as the Froude number. So here, this is the expression for Froude's number, and you can substitute the value of inertial force divided by the gravitational force. You will definitely get this Froude number. Okay, so now Froude number, what Froude model loss is, as similar to the Reynolds number. Reynolds model law, Froude number is if the forces, the inertial force and the gravitational force are predominant in a system, then for the model to be dynamically similar, the Froude model law has to be satisfied. It is very straightforward. And here, Froude number of model is equal to Froude number of prototype. These conditions must be fulfilled for model to be dynamically similar with the prototype. With this much of information, let's try to solve a small problem. In a model test of a spillway, the discharge and velocity of flow over the model were 2.5 meter cube per second and 1.5 meter per second, respectively. Calculate the velocity and discharge over the prototype, which is 36 times the model size. So here, what are the information provided? The characteristics of the model, the flow characteristics and the discharge characteristics of the models are provided. Also, the ratio, the length ratio is also provided in terms of scale, right? So we noted down all the information. Discharge of model is given, velocity of model is given, the length ratio is also given. So according to Froude model law, Froude number of the model should be equal to Froude number of the prototype. Now here we express this in terms of the formula, and from here we find the velocity of the prototype. Further, we can find the discharge. Discharge is nothing but the velocity times area, then express this in terms of a ratio, and most of the parameters are already known, and from here we can find the value of discharge. Now what I want you to do is you can investigate on the Euler's number, Mach number, and Weber number. This Euler's number is nothing but it is the ratio of inertial force to the pressure force. Mach number is the inertial force to the elastic force. Weber's number is the inertial force to the surface tension force. And Euler's model, Euler's number will give rise to Euler's model law. Mach number will give us Mach model law. Weber's number will give us Weber model law, and this can be expressed as the Euler number of model should be equal to the Euler's number of the prototype. So similarly, it applies to all other numbers as well. So this ends our chapter on dimensional analysis and the model investigation. Thank you for being here. Thank you.